Okay, well, thanks very much, and thanks to Stephen for the invitation for coming here. So, as he said, I'm actually an astrophysicist and cosmologist, and I got into geometric algebra over 30 years ago, and I use it a lot for things I actually do in gravitation and cosmology. And what I want to do today is to give you a sort of overview of where we've got to in applying geometric algebra in physics. And it's an incredibly useful approach to the mathematics of physics. The point is it allows you to use a common language in a huge variety of contexts. So there's just starting off with a partial list of all the different mathematical bits of apparatus which it can deal with and subsume and show how similar they are, and you just need one apparatus, the geometric algebra, to work with it. So it includes complex variables, vectors, quaternions, matrix theory, differential forms, tensor calculus, spinors, twistors. They're all subsumed in this common approach. So this gives you very great efficiency. You can quickly get into new areas. I've been able to get into areas I never thought I'd be able to approach because the mathematics just looked too difficult. But you don't need new mathematics to get into these areas. You can use geometric algebra, and that's just an incredible efficiency and gives you the opportunity to actually get to grips with the concepts in these areas without the maths being totally unfamiliar. And it does tend to suggest new geometrical, and I'll say therefore physically clear and coordinate-independent ways of looking at things. And you'll see that a few times as we go through some applications. It's not just, in a sense, it's a mathematical tool, it's a conceptual tool. And so you can think in a slightly different way about a problem and maybe get some geometrical type insight that you didn't have before, which will introduce some new ideas you could have about the physics. So what I want to do today is to introduce a few aspects of it in more detail, and this will be principally applications to electromagnetism, quantum mechanics, and gravity. And in fact, one could take this as a sort of subtitle for the lecture, the 4 fundamental forces of nature. How do we treat these in geometric algebra, and does it give us some new insights? And just a reminder, of course, these are the 4 forces. Electromagnetism, that's the force which keeps atoms together, the electrons in their orbits. The weak interaction, that's responsible for radioactivity. The strong interaction is what binds nuclei together, and therefore incredibly important to give us the building blocks of atoms. And then gravity, which stands rather apart from the others, it seems, but we'll show today how you can treat it in a way that makes it really look much more similar. Now, there's just a few people here, maybe, who haven't been to the preceding lectures, but I felt because of that I ought to give a short introduction to geometric algebra itself. So apologies if you've sat through this several times. I will go quite rapidly through this first bit, just explaining the very basics of geometric algebra. So we know that in complex numbers as a unit imaginary, I, its property is I squared equals -1. And of course this was a mathematical problem for several hundred years. People worried, what is this thing that could square to -1? Because no ordinary number does that. And so in the end they settled on an axiomatic definition and just asserted there is a number with this property, and complex numbers are of the form x plus iy, xy ordinary numbers. But consider this. Suppose we've got 2 directions in space, A and B. These are just vectors as usual. And suppose you had a language in which you could use vectors as words and string together meaningful phrases and sentences with them. So AB, BAB, etc. would all be meaningful phrases. And then you have just 2 rules. If A and B are perpendicular, then AB is minus BA, so they anticommute. If A and B are parallel, in the same sense, then AB is just the product of their lengths. So here's your rule for multiplying vectors in this case. And just this does an amazing amount of mathematics. Suppose you have 2 vectors, unit vectors at right angles, so they square to 1 and they anticommute. then this is the basic calculation now of geometric algebra, what we're just about to do, right? Everyone should make sure they go through this for themselves. It's very simple. Look at E1, E2 squared. That's E1, E2, E1, E2. We can anti-commute these two in the middle to get a minus sign. Then we have minus E1, E1, E2, E2, which is minus 1. And then suddenly, this sort of cuts through hundreds of years of mathematical problems. You have an object, a geometrical object, which squares to minus 1. And you can now see that complex numbers are essentially objects of the form x plus E1, E2, y. And we call this E1, E2 a bivector, and we think of it as an oriented plane segment swept out and going from E1 to E2. I've drawn them orthogonally here, but more generally, given any two vectors A and B, you can form A wedge B, where you sweep out over the angle between them, and this builds up to further dimensions like this. You start with a scalar. Here's a vector, directed line segment. Here's what we've just been doing, and of course these bivector planes have an associated orientation, and then you can carry on, take one of these parallelograms you've formed, sweep it out over a further vector, here C, and get an oriented volume. So you can keep going to as many dimensions as you've got. So let's look at this more formally. You've got a vector space with the usual inner product, and we've introduced this outer or wedge product to produce this bivector. And the essence of geometric algebra, this is what Clifford did, he united these two things into the single product called AB. So AB is A dot B plus A wedge B. And the key thing is that this product's invertible. That's why it's so good. Individually, you cannot invert these. You can't strip off A at the left, but here you can multiply on the left and remove the A from this. So in a proper development, what you do is you take the geometric product itself, this AB is primary, and then you write in terms of it the dot product as a half AB plus BA, the anticommutator, and A wedge B is a half AB minus BA. So that's how you get things going axiomatically. So moving up to 3D, which we already did when we saw how we swept out that parallelogram along a further vector. So now we have three vectors, all squaring to +1. They're all mutually orthogonal. And now we can form their wedge product, all three of them. That gives us I, the pseudoscalar, for the space. It's an oriented volume element for the space. And it's quite nice that if you take I times any vector, you get a bivector, because imagine we've got I times E1. Then the E1 vanishes. You just get left with E2. That should be E3, sorry. That's wrong. IE2 is E3, E1. IE3 is E1, E2. And now there's something quite interesting, because we squared E1, E2, which was the pseudoscalar of 2D space. We got -1. What happens if we square this thing we found, which is a trivector, which is a pseudoscalar of a 3D space? You work it out, you get -1. So this is quite instructive. We've now got another real geometric object which squares to -1. And the general lesson is there are many such objects which square to -1. In physics, people have tended to reach for little I, right, this uninterpreted unit, imaginary. They've reached for that whenever they've had something squaring to -1. And so it's ubiquitous in physics. But what this approach makes clear to you, you find out that in several cases, these little i's are masking something else. They're incorporating a bit of geometry, which you could have been using, and smuggling in this unit imaginary when it shouldn't be there, quite possibly. And in fact, it means you seldom have any need for complex numbers. Okay, we call the highest grade object in the space the pseudoscalar. It's unique up to scale. And the two further things we need to just be very clear on are reflections and rotations. As you've seen, several times, reflections, very easy to implement in geometric algebra. If you've got a vector A, you want to reflect it in the direction n to produce a new vector A dashed. It's really very nice. You get this sandwich product, A dashed is minus NaN. And just to give one more little example, again, this is something you should work through for yourselves, of a basic thing in geometric algebra. Why is that true? Well, let's take 2n wedge A times n. We know n wedge A times 2 is Na minus An. N squared is 1, so this is Nan minus A. And so if I now add into here n dot A inside that bracket, then these things combine to give me just Na, so this thing is 2NaN. But I'm adding 2A dot N to this, like that. You look at this equation, and in that equation is minus NaN is A minus 2N dot AN. So that's the essence of the sort of calculations you can do in geometric algebra. They're really quite simple once you've got these basic rules. And this is a really nice result. So as you've heard from other speakers, rotations, you can get to these very quickly because it's a fact that two reflections form a rotation. And so let's reflect in n and then in m. We do that like that. You can see that what piles up on this side is n times m, but you get the reverse order on the other side. And so you define a rotor, which does this, to be, in this case, the m times n. Rotations are given by A goes to R, A R reverse. What's this R reverse? That's where you reverse the order of these objects inside it. So R reverse is Nm if R is Mn. And so, of course, that means that R times R reverse is 1, which is the other criterion for a rotor. So this works in spaces of any dimensional signature, which is incredible. It's a real unification. And it works for all grades of multivectors. So it doesn't matter what A is, whether it's a vector, a bivector, trivector, whatever grade it's got, exactly the same thing happens to it under rotations, which is really useful. And then finally, on this first bit, we can have a general rotor by exponentiating a bivector in 3D. As we've said, we can get the bivectors by taking the I times a vector. And so in 3D, it's sort of accidental symmetry of the space in a way that you can always write a bivector like this as the dual of a vector. And so, of course, this was the reason for decades of misunderstanding about rotations. What you should always do is think of the rotation as being a plane, i.e. bivector, an oriented segment of a plane, and not a direction, this n, which has come in here. It's only in 3D that accidentally we end up with something that can be dual to a direction. So the bivector B is the plane of rotation, and a rotor is then a scalar plus a bivector, as you see just here. This ties in perfectly with the quaternions. Here's a quaternion, here's its definitions, and we get a complete map between the two like this. All you have to worry about is that the J in quaternions is actually minus IE2. So people doing quaternions versus people doing this E1, E2, E3 algebra, there's actually a change in the handedness between the two. Okay, that was the introduction. Now, let's go to space-time. So this is effectively the new bit. So in space-time, we want to construct the geometric algebra corresponding to it. We'll be looking at preserving this invariant interval. So this is the equivalent in Euclidean geometry, right, of x squared plus y squared plus z squared. When you go to relativity, the thing you want to preserve under transformations is now here. S squared is c squared t squared minus x squared minus y squared minus z squared. And we're going to work in natural units where c equals 1. So I think you won't see another c anywhere else in this presentation. It's far more sensible always to have c equals 1, speed of light. So now we need 4 vectors. And looking at this, we can see how they need to square. E naught squared, the time vector, is going to be 1. E1 squared is minus 1. E naught dot Ej 0, and Ei dot Ej is minus the Kronecker delta. What's going on there? We're just saying that the spatial vectors, because of this signature we've used here, are going to square to minus 1, and everything's orthogonal. And you can summarize that in this way. In relativity, you normally use suffixes, Greek indices, which run from 0 to 3, call those mu and nu, then E mu dot E nu is the diagonal plus minus minus minus. That's called the Minkowski metric, and written E to mu nu. Let's now start forming bivectors from these. There's 6 bivectors in the algebra that you can get, and they divide into 2 types. So there's one type containing E naught, and they're these, EI wedge E naught for I equals 1, 2, 3, and those not containing E naught, and they're like this, EI wedge EJ. And how these differ, why they're singled out in this way, is they have different squares. So here's a general result. For any pair of vectors A and B with A dot B equals 0, then A wedge B squared, because they're orthogonal, we can write that as AB, so we have AB, AB. If they're orthogonal, we can flip the A and B here, we get minus ABBA, and then that's equal to minus A squared times B squared, because the B in the middle just becomes B squared, and we've got the A outside, so that's minus A squared, B squared. So going back to these bivectors here, we can easily work out what they square to, and the ones that don't have the E naught, you square those up, you use this rule here, they go to minus 1, and because we've effectively flipped sign, our Euclidean part, we've got the opposite signature, but it's just how it's generally done in special relativity. It's the time bit which has the positive signature. These are actually Euclidean, all right? And they're just the ordinary, they generate just ordinary rotations in a plane, as we've been discussing. The time-like bivectors are the ones which got the E naught in. They square to plus 1, and they generate a hyperbolic geometry. So when you exponentiate these, like this one I've got here, e to the alpha, E1, E naught, you expand that out, it goes to cosh alpha plus sine alpha, E1, E naught. Whereas if I exponentiated something without an E naught, it would go to a cos and a sine. And of course, this is crucial to the treatment of the Lorentz transformations, and we'll look at that in a bit more detail soon. How about the highest grade element of the space? Well, that's the pseudoscalar I, which is E naught, E1, E2, E3. It's grade 4. Now, any grade 4 element is always going to reverse to itself, so I reversed, you work it out, that's equal to I. What does this one square to? Because we should work out for each element we get to what its square is to understand it a bit better. I squared is the same as I reverse. You work that out, and again we get minus 1. So here's yet another thing that squares to minus 1, but again is a separate geometrical entity. So if you multiply a bivector, any of these bivectors we're talking about, by I, then you get a grade of 4 minus 2. This is duality, which is 2, and so you get another bivector. So I transforms bivectors to bivectors. And in doing that, it provides a map between bivectors with positive and negative square. So just an example, here's a spatial bivector, here's a bivector involving the E naught, so this is time-like. So I, E1, E naught is the same as E1, E naught I. I anticommutes with each vector. So when you've got 2 vectors, as in a bivector, it commutes. I commutes with all even grade elements. And you work that out, you get minus E2, E3. And this is one of these, what we call spatial bivectors, which square to minus 1, these square to plus 1. And of course that makes sense, because one's got I in, and the other hasn't, and the I squares to minus 1. So how about vectors and trivectors? There's 4 of these, and they get interchanged by duality again. So I moves bivectors to bivectors when you multiply, and if you start with a vector, like here, we've got I, E0, that's the same as E1, E2, E3, with a minus sign. And I've already said I anticommutes with vectors and trivectors, and always commutes with the even grade elements. Now, we've called everything E so far. What we're going to do before carrying on is we're going to settle on some given fixed Cartesian frame of vectors in which to do our physics. You can think of this as a laboratory frame, and we're going to rename our E mu as gamma mu, right? So you'll see very shortly why we do that, why we call these things gamma mu. And we're basically done now. We now have available the basic tools for relativistic physics, which we call the Spacetime algebra. And here's the ingredients. We have 1 scalar, 4 vectors, the gamma mu's, mu 0 to 3, 6 bivectors, 4 trivectors dual to the vectors, and a single pseudoscalar as shown there. And so we're using this new name. Let's take the dot product of gamma mu times gamma nu, and we know that's the Minkowski metric, the eta mu nu that we talked about before. That's how we set everything up. And so in particular, let's expand that out. We know that gamma mu dot gamma nu is gamma mu nu plus gamma nu mu, and the dot product has a half, so bring the 2 up here. And here's why we call them gammas, because for people who do relativistic quantum mechanics, this is the defining relation of the gamma matrices that Dirac invented. Well, he didn't actually invent them quite in this gamma form, but they're the key to doing relativistic quantum mechanics. And so we got to the Dirac matrix algebra, and that explains the notation, because these things will be matrices in relativistic quantum mechanics, and they're always called gammas. But for us, they're just vectors. They're not a set of matrices in isospace. They are actual vectors. And so you get, this is the first sort of astonishing thing that happens. These matrix representations for relativistic quantum particles, which people in the field are extremely familiar with, turn out to be just the basis vectors of 4D space, which is very striking that that happens. Now, suppose we're in some inertial frame. In that frame, it's possible to define a set of relative vectors, and these are space-time areas swept out while moving along the velocity vector of the frame. So I've illustrated that here. The velocity vector of our frame is gamma naught. We start with the vector gamma I. We sweep it out. As time passes, it gets swept up here to some new gamma I. And in that sweeping out, we develop a bivector, which is an oriented plane segment. And we label that sigma I. All right, so this is the definition. Sigma I is gamma I times gamma naught. So the spatial gamma vectors multiplied on the right by gamma naught give you this sigma I. And of course, they're actually space-time bivectors, but they can function as spatial vectors in the frame orthogonal to gamma naught. And again, this is quite an interesting idea that as human beings, we're not used at all to the idea that we're actually shooting along a time axis at the speed of light. At any moment, that's what we're primarily doing. We're moving extremely rapidly up the time axis. And so these vectors, which we have around us, Cartesian basis vectors in this room, are actually being swept really rapidly. And so it's very interesting that in the 4D way of thinking about that, they're bivectors, because that's sweeping out, but coming back down the other way, we can use the gamma naught to define these things that are actually vectors for all intents and purposes in this room. So What about these sigma i's? It's easy to show from what we've already defined that they satisfy this. Sigma I, sigma j. Again, we just take this anti-commutator product, sort that out. That comes to, since it only involves the spatial gamma i's, it comes to delta ij. So their dot product is delta ij. And if you work out the the commutator, it's easy to show that's the alternating symbol epsilon ijk times I sigma k. So actually, these sigmas we've defined are precisely satisfying the same relations as the Pauli spin matrices. So I've done this an unusual way round. People normally do Pauli quantum physics and Pauli spin, and then you work up to the Dirac equation. Here, we're starting with Dirac physics and then coming down and finding, oh yes, we can define these relative vectors which satisfy all the properties we need for the Pauli spin matrices. This displays the matrices explicitly, the hats indicating on these quantities that they are matrices. So, okay, I've said this is the same as the algebra of the Pauli spin matrices. What you can also observe are these relations are precisely the same as the relations for an E1, E2, E3 type frame with things squaring to +1 in 3D space. So actually we've recovered the geometric algebra of 3D space in this relative space form. We've got it just by basically multiplying on the right by gamma naught. And now, a particularly nice feature of this is that there's a bit of economy that happens here. The pseudoscalar of the 3D space, which is sigma 1, sigma 2, sigma 3, you work that out, and it comes to the same as the pseudoscalar of the 4D space. It rearranges to give this thing we called I. So basically, the 3D subalgebra shares the same pseudoscalar as space-time, which is quite an interesting realization. So we've got this picture here that we've ended up with, where we can have at the 4D level the full algebra, 1, the gammas, sigma I sigma I. So there's 6 altogether of those, I gamma mu and I. And then if we just take the even space, so the scalar, the bivectors, and the pseudoscalar, as we drop down, these ones here, the sigma i's, end up here as the basis vectors, so odd elements of the 3D space, and these ones here become the bivectors. So this is very neat. It means that, again, starting at 4D is the way to go, because then we come down and find out that we have this algebra for 3D space using this even parts of what we had in 4D space. And that's an observer-dependent split, which makes sense because each 3-frame we work with is relative to some observer will have a velocity. Now, let's look at the Lorentz transformations, which is where relativity started effectively. So how you'll probably, if you've worked with Lorentz transformations, you'll probably have seen them looking like this, which is not very friendly, but basically it's all seen as a coordinate transformation. You have some coordinates, t, x, y, z, for an event in one frame, and you want to calculate those coordinates in a new frame. This shows it for just the t and x components, and the apparatus you need is this gamma factor. It's not to do with any of the other gammas we've had. That's 1 minus beta squared, all inverse square rooted, and beta's the scalar velocity, so v over c. So that's what it looks like. And when geometric algebra starts to work on this, the first thing you think of is what's invariant, what's the geometrical object? And so the geometrical object is a position vector of where some event occurs. And it shouldn't matter which frame you use to express that. So that's got to be the same in a frame e mu or in a frame e mu dashed. And so in particular, x mu e mu equals x mu dashed e mu dashed. Now, I'm just going to give a little aside here, because it's relevant to what happens in a little bit. The relation of coordinates to these frames comes from the notion of reciprocal frame. This is another extremely important part of geometric algebra and physics. given a frame E mu, you can define the reciprocal frame E upstairs mu, right? This one was downstairs, this is upstairs, like this. You start with your downstairs frame, and you demand that the upstairs frame, when it's dotted into it like that, gives you the Kronecker delta. So you've got orthogonality to the downstairs frame in the upstairs frame. And it's normalized orthogonality because it's 1 on things that, indices that match. So in particular, the gammas that we've been looking at, since they square to something negative, or they square to -1, in their downstairs frame, the upstairs frame introduces a minus, whereas the gamma naught doesn't flip when you go upstairs. And so with these definitions of reciprocal frame, then it turns out you get upstairs coordinates like this, where you just dot the position vector with the upstairs frame, the reciprocal frame. So in particular, the time is E upstairs 0 dot position vector, and the time dashed will be E upstairs 0 dashed dot the same x. All right, so in this approach, we just think of events in space-time, and they're labeled with a position vector, and then it's up to us how we peel off coordinates from that position vector. As I'll show you shortly, this whole thing is very useful for working with curvilinear coordinates if you happen to have those, and articulates extremely well with geometric calculus. Okay, so concentrating on the 0, 1 components, we've got t E0 plus x E1 must be t dashed E0 dash plus x dash E1 dashed. Now, using these relations here, the Lorentz relations, it turns out if I then use those in these expressions here, you can peel off the E0 dashed is this gamma factor times E0 plus beta E1, and E1 dashed is gamma E1 plus beta E0. Now, I would regard this as totally a backwards way of doing it, because this is the thing that is actually obvious, because where this comes from is jumping, I'm just going to jump to this to show you. It comes from taking your initial frame and acting on it with a rotor to get the new frame, where the rotor in this particular case, if we have a velocity in the one direction, is e to the alpha E1 E0 over 2. It's that hyperbolic transformation we looked at before. And this just goes through making sure how one understands how alpha relates to beta. Beta is the ordinary velocity. It turns out that that's the same as tangent of this hyperbolic angle alpha. And so what's this gamma thing that we had back here? Okay, what's the gamma? That is, shown just here, that is 1 minus tangent squared alpha to the minus half, which is cosh alpha. And so that means the E0 is, which we were able to peel off from here by going in this direction, that is equal to cosh alpha E0 plus sine alpha E1, and that is the same as e to the alpha E1 E0 times E0. Similarly, the other one, the E1 dashed, is equal to this times E1, and if you look at the fact that the E2 and E3 frames don't change at all, you deduce a transformation in this form. Of course, that's because we're starting with the Lorentz transformation itself. That looked quite complicated. By far the easiest thing is always only to work with this sort of approach, where you rotate your frame vectors, and then you can read off things like this if you absolutely have to. Let me give you an example of that in a moment about how useful this approach, where you start like this, it is. Basically, the same rotor prescription works for boosts as well as rotations. Boosts are where you've got a velocity in a particular direction, and it makes space-time a unified entity. And you can generalize all this to R equals e to the b, where b is any bivector in the space-time algebra. And this gives you fully general Lorentz transformations. And again, given any object in the algebra, you just rotate it in the same way. M dashed is R, M, R in reverse. So let's try and actually use this in something that you may have come across. And this is in the context of Lorentz transformations in electromagnetism. So electromagnetism deals with when you look at it relativistically, is a thing called the Faraday. So I'm just writing here the conventional Faraday tensor, which is an antisymmetric 4x4 tensor. We'll see shortly sort of what it really is in geometric algebra. So as a matrix, it's got these components where what's happening here is you've got the E field. They go on the top row and then down the first column. And then on in these positions here, the positions which are off the diagonal, because this is antisymmetric, we have the magnetic field, Bx, By, Bz, in that particular arrangement. Now, that is how people doing relativistic electrodynamics think of the field strength tensor, the Faraday. They think of it as this matrix. You often see this, but it hides the natural complex structure. In our version, F is a spacetime bivector, and you generate it from the electric and magnetic fields E and B, which are relative vectors in the 3-space orthogonal to the time axis. And I'm going to use these bold letters for a relative vector. And that means, since they're relative vectors in this space orthogonal to the gamma naught, therefore they're interpreted in the SDA, they're actually bivectors. So these E and B fields are actually bivectors. And what's the Faraday? It's just this. It's E plus IB, where I is the pseudoscalar for 4D space. And this gives suddenly all sorts of wonderful intuition about what's going on with electric and magnetic fields. They were never properly vectors. They're these relative vectors which become bivectors in the full 4D field. And when you're thinking about the difference between them, it's because these ones involve the gamma naught, and these ones, being of the form IB, don't involve the gamma naught. That gives you the difference between magnetic and electric fields. If you want to go back to the matrix elements, you can get them very simply like this. The components F mu nu, gamma nu, wedge gamma mu, dotted with F. And this is very characteristic. You take a geometric algebra thing, like here, F, and if you really want to get components out of it in some sort of standard tensor calculus type way, you can, and it's generally done by things like this, dotting with the gammas. Now, how can we recover E and B individually? We can do it if we know gamma naught, if we know the velocity vector of the frame, and that's because if we surround F with gamma naught, you get, because it can't pass through the E without flipping, because the E has got a gamma naught in it plus something else, then it flips to minus E, whereas this one, it passes straight through. And so you can recover the E and IB individually like this. E is a half F minus gamma naught F gamma naught. IB is a half F plus gamma naught F gamma naught. Just hold on to this thing about gamma naught F gamma naught to right near the end. We'll find out this is crucial in the strong force that we talked about that binds nuclei together. Anyway, here, the split into E and B depends on an observer's velocity, and if you had a different observer moving with a different speed, like this, so if V is R gamma naught R reverse, they'd have a co-moving frame gamma mu dashed, given by you take all the frame vectors, you rotate them in the same way. What would they see for the electric field? Well, you can work that out because they've got a sigma I dashed, dotted with F. Again, here's the recipe. There's just a single geometric entity sitting there. But if you insist on knowing what its value is in a particular frame, you just dot with that frame. You work that out. That's the same as back in the original system, the sigma i's, the back-rotated Faraday. So all we have to do to get the new electric field strength is back-rotate the Faraday and dot it with the original sigma i's. So you get exactly the same transformation laws for vectors, i.e. this rotor thing. It's very efficient. And for example, let's carry out a case. Let's have stationary charges in the gamma naught frame set up a field like this, just pure electric. F is E, Ex sigma 1 plus Ey sigma 2. We have a second observer. They have velocity tangent alpha in the gamma 1 direction, and so the relevant rotor is the one we talked about before. It's E alpha sigma 1 over 2. And let's apply that to F. So we take that, we apply it backwards, as I've just shown you, to get the components of the new frame. And so let's put that row to either side of this. The sigma 1 will just float straight through that. We won't see it. And then the e's will, because we got an R reverse here, one of these has got a minus, one's got a plus. And so you just get no change in the sigma 1 component, which is the E field in the x direction. The other one, though, as it goes through the sigma 2, you pile up an e to the minus alpha sigma 1. And so if we write this in terms of cosh and shine, we can identify then that the electric field is unchanged in the y direction. We've got a cosh, right, expanding out this exponential of the sigma 1 for the y field, and we've got a new bit. Because we've got, when I expand out this exponential as cosh and shine, the sigma 1, sigma 2, they're going to hit each other and give me an I sigma 3. What's an I sigma 3? That's a magnetic field in the z direction. And so in this very elementary way, you find out that the motion induces, because you had a y field in the electric, y electric field, it induces a magnetic field in the z direction. And so you can really understand why you've got this happening, and it comes down to a bit of Clifford algebra, very basic, that sigma 1, sigma 2 is I sigma 3, is why this z component of a magnetic field is induced. Now, this sort of thing is very nice, I find, because it's completely sort of rock solid conceptually. We know that all we're doing is this, and then you work it out and you get some definite answer and you feel confident in it. This is really quite different from what you get if you've ever tried this in conventional approach. These sort of calculations take pages to do in standard tensor component approaches, and you generally don't feel very confident at the end. So actually, it really is the case. This is definitely much simpler than working with tensors. Okay, so that was the first little look at electromagnetism. We're going to come back to that shortly, but to do that, we're going to need an additional entity, which is the derivative operator. And how do we do that? We do that using this reciprocal frame we discussed above. We said if E downstairs mu is a frame, then the reciprocal frame E upstairs nu is defined like this, which we went through. And just to emphasize here, these upstairs things are vectors just like the E mu. They live in the same space. People sometimes get confused about this and think, oh, well, you're defining a one-form space. We're not. These are just vectors in the original space, but they have this relationship with the downstairs frame. So let's define a vector differential operator. We'll use E mu equals these gamma mu's, this Cartesian frame, to start off with. Here's the definition. The gradient operator is the gamma mu upstairs d by dx mu, like that, where the x mu are the coordinates. And I'll often write d by dx mu in this simple way of a partial with just a mu at the bottom. That's d by dx mu. And you can see that this operator combines the features of a derivative, obviously in the partials, and geometric algebra in that it's got these gammas. Now, so as things go on, and maybe some of it starts to look more complicated, just as a quick encouragement, with just this object and the STA that we've done so far, you can basically do all of electromagnetism and quantum mechanics right through to electroweak theory without introducing any new mathematics. All right? So it's quite a strong claim, but I think you'll find it's true. So just to say, the definition of gamma here, the derivative operator, did not need to use rectangular coordinates and the orthonormal system gamma mu. You can do this for any arbitrary coordinate system, x mu. For example, suppose we were working with spherical polars in space-time. That would be t r theta phi, would be our x0, x1, x2, x3. That would be fine. Because what you can do, you can get these reciprocal frames in a very nice way from either the position vector x or from the coordinates x mu. How does that work? It turns out the downstairs frame is the partial derivatives of the position vector x. The upstairs frame is the gradient, the derivative operator, acting on the coordinates. All right? So you can work this out for yourself. Have a go at this. Define like this, all right? So I've got coordinates, and I express my x position vector in terms of them. The downstairs frame E mu is the d by dx mu of position vector. The upstairs frame is the gradient of the coordinate. They will satisfy this reciprocal frame thing. And in that setup, the geometric object grad is given by E mu d by dx mu, which we can write like that. So it becomes really easy. Because you've got access to this reciprocal frame, it's just no worse than you had with the gammas. And I should just say, when you've got this reciprocal frame and you want to get the components of a vector, it couldn't be simpler. The upstairs and downstairs components of a vector are A upstairs, sorry, the vector is A upstairs mu is A dot E mu, and A downstairs mu is A dot E mu downstairs. Now, it says here, these statements look trivial. They're actually enough to do everything associated with vector calculus in curvilinear coordinate systems. I don't know if anyone's actually tried to do this. You get this often, for example, in fluid dynamics, and also some electromagnetic cases, where you want to work in some general curvilinear coordinate systems, and the tensor calculus identities, you need to do that. Are generally pretty difficult and can take pages of work. This cuts through the whole thing, and I've written everything you need to do it right here. Okay? So this is one of the most useful bits of the geometric algebra approach that one can have that is just widely applicable. You don't, once you've got this in your head, then you never need worry about things like curvilinear coordinate systems and any special identities that you might think you need for that. It all goes away. Okay, so what we're going to do now is we're going to split up the gamma. I keep calling it gamma, I'm sorry. This would be del or nabla if I was giving it a Greek name. Let's just call it the derivative. We're going to split that up by multiplying it on the right by gamma naught. This will cast it into a relative form. Let's do that. You find out that that's d by dt minus sigma I d by di. This bit here is quite clearly, since the sigma I are their own reciprocal frames, say square to plus 1, that's dt minus what I call a bold grad. The bold grad is what I've got here, sigma I d by di. So that's the relative 3D vector derivative. Again, that's very useful. You can use that in fluid dynamics and things like that if you're just in a 3D application. In that context, okay, what I'm doing again is backwards, right? I started with the Lorentz transformation and moved forward to show you, with just rotors, whereas in reality what you should do is start with the rotors and derive the Lorentz transformation from that. Here I'm going to start up with the standard split-up form of Maxwell's equations, written in using these operators, and here they are, right, for Maxwell's equations. You can rewrite that in this form here, right? They reassemble using the properties of the geometric product to that. Well, you notice that it's reassembled to bring in this E plus IB that we said was the Faraday. J is the current, which we had coming in this equation here. Bold J is the 3D current. We now define a 4D current like this. We write scalar plus relative vector J, and we put a gamma naught on the right. That then reassembles to being a space-time current vector J, and you get this beautiful single covariant equation for Maxwell's theory, right? This is the whole of all Maxwell's theory in electromagnetism, all in that equation, right? Grad F equals J. That's very beautiful. Does it actually help you at all? And it really does. And it's this crucial thing that the geometric product has, which is the invertibility. So the advantage here is not merely notational. just as the geometric product is invertible, unlike the separate dot and wedge product, the geometric product with the derivative is invertible via Green's functions, where the separate things that this would have a grad dot, which would be a divergence, and a grad wedge. You can't invert either of those. So this led to a new method of solving some electromagnetic equations, which Crestran and I worked on. This is an example. I don't have the animation for this one. I'll show you an animation of another thing soon. But the basic idea here was that we laid down a set of mirrors in a plane, and we illuminated this with a beam of radiation. And this shows the mirrors reflecting that radiation. That doesn't sound very hard. The point is this is exact. This has got all the diffraction effects coming in. You can see some diffraction effects occurring in this. And the particular feature about this was that we set this up so the user, person who wanted to play with this, could change the angle at which the beam went in and hit these mirrors just in real time. And then you could just watch this thing respond immediately in real time. And that was possible because we were able to sort of take off this grad and define an underlying structure which was pre-computed, and then you could just apply the beam of radiation to it. And that was effectively a new technique. Okay, so here's a second example of electromagnetism. I want to consider radiation from a moving charge, and in this particular area is David Hessel's, who pioneered the techniques on this some years ago. So these equations are basically due to him. And the final form of this Faraday that you get to is, I think, definitely the most compact and informative of any that have ever been achieved. If you've ever read the Feynman lectures on physics, he starts one of the volumes saying he's achieved this really nice compact form for the radiation from a moving charge. I think this one is much better and more intuitive. So now, don't worry if you don't follow the details. I just want you to get a little idea of what goes into it. So one of the Maxwell's equations, if we peel off the trivector part, is grad wedge f equals 0. That has the implication you can introduce a vector potential like this. F is grad wedge a. It's because the grad wedge grad is 0 that you can do that. You then go into what's called a particular gauge, div of a equals 0. That's just a gauge choice for the A to make things simple. So that, because it makes it simple, because then F is just grad of A. And so if you want to calculate grad of F, which is going to be the input current, then that's just del squared of A. So you've got a nice wave equation. In this setup, the idea is that you have an observer, a position vector x, and you have a particle going along some path, which we write as x naught of tau. The naught here means that's a particle. The tau is the proper time of the particle as it moves along the path. And we've drawn this light cone here because what you get at a position x corresponds to where the path of the particle hits your backward light cone. That's where any information about the particle has to reach you along this null vector. I call it big X, which goes from one position to another. So big X is position vector x for the observer minus the x naught of the particle. That has to be null. Now, the first beautiful thing is, again, I don't know if you've ever been through this, the Lienert-Vicha potential is a solution to this problem, but it's quite difficult often to get it right and notate conventionally. This is the full answer in the geometric algebra. A is q over 4 pi, that's just units. Here's the relevant bit. The velocity of the particle, v, at this point, over x dot v, that's the full Lienert-Vicha potential which solves this problem. And this is true no matter how complicated the motion. But we want F, the Faraday, which is grad A, and you need a few differential identities, and there's one really interesting one that comes out. I won't go through the derivation, but basically, because x squared is 0, if you differentiate that, you find this rather interesting relation here. you find that x squared equals 0 tells you that the grad of the proper time is equal to this x over x dot v. And that's something a bit strange here, because what I mean by the grad of this proper time, how do I interpret a proper time as a field which I can take the gradient of? Well, the point is, if I go back here, at every x, as I move around in space here, you intersect the backward light cone. Your backward light cone intersects the path of the particle at a different tau. And so as you move around, that tau changes, and so it's like having a field. And you can find its gradient just here. This is just an example that not everything that's a field has to be interpreted as being a sort of physically real thing which carries energy and so on. This is called an adjunct field when this sort of thing happens. Well, proceeding, what we do is we define the acceleration bivector for the particle. That turns out to be v dot wedge v, which is actually the same as v dot v. These are all orthogonal. And here's the result for f that I promised. So this is the complete radiation field of that particle, and ignore the denominator for a moment, it's x wedge v plus a half x omega v x, and the omega v, as a reminder, is this acceleration bivector. This first bit, the x wedge v over the denominator is x dot v squared, that's actually just the Coulomb field in the rest frame of the charge. So this is not radiation, this is the Coulomb bit. This bit here is the radiation. It's q over 4 pi, half x omega v x over x dot v cubed. And how do I know that's radiation? And what I'm going to do here, again, illustrates some of the efficiency and ease of use of the geometric algebra here. The way you prove it's radiation is to show that there's a contribution that it makes to the energy at infinity. So we have to work out the energy of this radiation, and you need something called the stress energy tensor or energy momentum tensor to do that, which in this approach just becomes a linear function of some input vector, A, and here's the linear function. It's very beautiful. It's the reflection of the input vector to the stress energy tensor in the Faraday itself. You take minus a half FAF. That returns a vector, and that tells you the flow of energy. Again, if you've ever seen the conventional forms in tensor calculus for this stress energy tensor, you'll know they're really complicated. So this is really very pleasant to work with instead. It turns out that bit drops off as 1 over distance squared, and so when you're integrating it over a sphere, which goes up in area as the distance squared, you get something that doesn't vanish, and that's this radiation component here. So what you can do is, along the lines of what I was telling you we've done with the mirrors, where we changed the input radiation field in real time, what you can do is have a go. Let me just find the demonstration. So this is going to calculate the Faraday field for particle, that we're going to control where that particle is by using a mouse in 2D to drag around where the particle is. So let's have a look at that. Oh, annoyingly, it loses the place. There it is. So let's get rid of the current cursor. What you're seeing here, I'm afraid it's a bit hard to see, this is the mouse position, and that's where the charge is, okay? And we're moving that charge around at will, and what's following it is the radiation field. You can see that there's always a lag, because as the charge is moved, the observer at that point doesn't find out about it until a light travel time delay has occurred. Now we're starting to do something interesting. We're starting to wind up the radiation into a circular form, we're going to make it tighter and tighter, and eventually it becomes pretty much like synchrotron radiation. So doing that computation is something that is really quite tough to do conventionally, but you can just write down really simple equations, as I've shown you, and it just takes a few lines to be able to do that in this geometric algebra formulation. I'm not sure my son would like emphasizing how easy it is. So he actually did that when he was still at school as a little simulation, just using some simple geometric algebra programs. So, it really is something that anyone can try once you've got that in hand. Okay, so let's go back here. Right, so that was electromagnetism. Now let's get started, if people are up to it, on quantum mechanics. Okay, so electromagnetism, one of the four forces. We're going to now move off towards the ultimate aim being electroweak and strong forces. Along the way also will include gravity. So, what does spacetime algebra bring to this? We find that the algebraic structure of wave mechanics arises naturally from the geometric algebra of spacetime. It allows you to reformulate standard quantum mechanics in a more geometrical way and suggest new lines of interpretation. And we'll get started by looking at what are called Pauli spinors. So this works conventionally by regarding these Pauli matrices as being matrix operators on column vectors. All right? I don't know how many will have done this, but in basic quantum mechanics of spin, you introduce these things here, which are called Pauli spinors. These are column vectors. They have entries psi1 and psi2, each of which is complex. And so you've got 2 real degrees of freedom in each, so there's 4 real degrees of freedom overall. And then you operate on them with these Pauli spin matrices that we've already looked at. Okay, so you have the structure of matrix acting on a column vector. Now, something quite remarkable happens in the geometric algebra approach. You can replace both objects by elements of the same algebra. And so space-time objects and the relations between them can replace all these single particle quantum statements. All right? So what we have to understand is how to model the Pauli and Dirac spinors within the space-time algebra. Now, this is a bit detailed probably. I just wanted to show you there's concrete stuff underneath this. What we do is we peel off the 2 degrees of freedom in psi1, call that A0, and as it turns out A3, the 2 degrees of freedom in psi2, which we call minus A2 plus IA1, and then the translation from the conventional Pauli column spinor through to the STA object psi is as shown here. Right, I've told you what the elements are in here. They line up like this. This gives you A0, the scalar bit, plus AK I sigma k. So we have scalar plus bivector is the psi. And this is common. Exactly the same thing happens for the Dirac case. It's the even subalgebra of the space, which is actually the spinors, which is an amazing revelation, actually, because spinors are assumed to be living in some completely different space, different part of mathematics. It turns out they're just the even elements of the geometric algebra of whatever dimension space you're in. So, for example, spin up state is just scalar 1, spin down is minus I sigma 2. And the action of the quantum operators on the states has got an analogous operation on the multivector psi. It happens like this. This is the translation. This Pauli spin matrix, sigma k hat on psi, is the same as operating with sigma k, our sigma k on the left, and a sigma 3 on the right. So you always use sigma 3 on the right, but what you're doing at the left varies with the operator. And you need the sigma 3 on the right to ensure that this thing stays in the even subalgebra. And verifying that this is all correct is basically a matter of computation. For example, if I apply sigma 1 hat, you get this column vector. That translates through to this equivalent which you can compute, is exactly the same as sigma 1 psi sigma 3, which goes in with this thing here. So again, this is something, I mean, I don't know if you've ever thought about venturing into quantum mechanics of spin. It's increasingly important technologically. This gives you a means of doing it just using the same geometric algebra you would use in, for example, in computer graphics. Well, this is actually a simpler version. This is just the 3D ordinary algebra. So we need a translation for multiplication by the unit imaginary. So the unit imaginary in quantum mechanics is not thought to have any geometrical meaning. We can find out what it does mean. If we take the three Pauli spin matrices, multiply them together, then we find out that you get I down the diagonal. Let's see what it gives here. So the translation of that would be sigma 1, sigma 2, sigma 3 on the left, and of course sigma 3 cubed on the right. That boils down to psi I sigma 3. So we discover that multiplication by the unit imaginary conventionally is the same as putting I sigma 3 on the right. So this is very interesting. This is yet another version of something that squares to -1, and it has a different geometrical interpretation. It's multiplication on the right by I sigma 3. And exactly the same happens in the Dirac case. So now you carry on. You can define a scalar. If you take psi times psi reverse in 3D for something that's just got even elements in, that always gives you a scalar. And then you find this rather magical thing. The spinor psi decomposes into this scalar square rooted times a rotor. The rotor is rotor -1/2 times psi. And this multivector satisfies R reverse as 1. And in this approach, Pauli spinors are simply unnormalized rotors. So you start realizing that the quantum mechanics you've been doing, which looks as though it's written in entirely sort of foreign mathematics compared to the mathematics of ordinary three-dimensional space, actually it's using just the same things, ordinary rotors in 3D space. And other concepts become quite simple. For example, the Hermitian adjoint, which you need if you're going to form the inner product of quantum states. Quite generally, it corresponds to reversion followed by reflection in the time axis. That's what you discover in geometric algebra. If we move the time axis gamma naught through this psi, because it's even, nothing happens. So you just find that the Hermitian adjoint is equal to the reverse in this case, which is nice and simple. Here's how you do inner products in quantum mechanics, and this is how it translates through to the space-time algebra. And I won't go into the details of this, but basically it projects out the 1 and the I sigma 3 components of psi reverse phi. These angled brackets on the right, Hugo was using them this morning with a little number down here to indicate that you're pulling off a particular grade. The convention I use is that if you're pulling off the scalar part, you don't bother putting the 0 to the right. But basically, these are just the scalar part of the thing inside the brackets. So this can start making sense of some quantum mechanical things that look rather difficult. So let's form the expectation value of the spin in the k direction. That's where you sandwich the sigma k Pauli matrix between versions of the psi, right? So this is the same state. We're asking what's the spin in this state quantum mechanically. You work that out, you find it's the same as the scalar part of sigma k times psi sigma 3 psi reverse. Well, that thing there is a vector. Let's define it as a vector, S. And what you find is that taking this expectation is the same as finding the kth component of S. So the quantum mechanical apparatus, which looks really forbidding, is actually telling you, oh, just find the kth component, which is very interesting. So I'm just reiterating that. Basically, if I pull out the row, I can find that my S, the spin vector, is R sigma 3, R reverse, and then scaled in this way. So, for example, suppose I rotate my laboratory apparatus through a new rotation r0, so S would go to r0, S, r0 reverse. That composes with the r embedded here to tell you that r goes to r0, r. And so this tells us about how we have this thing which is very mysterious in quantum mechanics about the transformation laws of spinors. We can understand now that they transform differently from other things. They only transform on one side, right? So psi would go to r0 side because the r builds up there, because the spinor is itself a rotor. And so that's why it only transforms on one side. So this explains the spin half nature of spinor wave functions is because they're actually rotors. You might be worried that picking out sigma 3 breaks the rotational symmetry of the theory, but actually this is not the case. And we can give an example from rigid body mechanics to illustrate that. What's going on is it's exactly like, right, let's just go back here. We're rotating a fixed vector sigma 3 to get this angular momentum vector of the particle. And that's exactly like in rigid body mechanics. We set up some fiducial fixed copy, reference copy of our body, and then we use a rotor to move it off to whatever orientation it has. And of course, in rigid body mechanics, there'll be some position path that it follows, that the center of mass follows as well, which we call x0 t. For the purposes I've got here, the important part is that you take x as some coordinate position vector in the reference copy of the body. How do you get over here? You actually use this rotor to move the fixed reference thing through to the outside world. And it's exactly the same here, right? We move the fixed sigma 3 through to where the S is actually pointing. And so here's our picture of what the Pauli spinor does. It's basically an instruction to take this fixed frame here, which has a sigma 1, sigma 2, and sigma 3, and it transforms it to the spin vector. And these other two vectors, I haven't gone into it here, but what are these other two vectors? Well, they don't matter individually. What matters is rotations about this. We saw that there was something that rotated about it. That was the imaginary, which was I sigma 3. So where these vectors lie in the plane is the phase of the wave function, the overall global phase. And so we've got an understanding then of the things that seem really quantum mechanical, the spin vector and the global phase, just in terms of where these axes end up. Now, what I'd like to do now is just say a few more words about the rigid body mechanics, because I want to show you a solution within rigid body mechanics, which is going to parallel exactly a solution that we have in the Pauli theory. So Hugo was talking about this sort of thing earlier in the conformal geometric algebra. We can extract an inertia tensor given information about where the material in the body is situated. The inertia tensor is defined like this. It operates on bivectors, and it returns another bivector, because this thing here, the x dot b, effectively gives you velocity. X wedge, that gives you angular momentum, and the rho tells you where the material is concentrated. That's shown in here. So the body rotates at angular frequency mod b, momentum density is this, and the angular momentum density is x wedge. You integrate to get the total expressed in the reference body. That's all in the reference body. You have to move it off to where the body actually is in attitude, and that's given by this rotor r we talked about just now, which rotates the angular momentum in the reference body off to give you the space angular momentum. So for a free case with no external couple, you can differentiate this with respect to time. You should get 0, and it turns out you can get this in just a few lines, that I on the time derivative of omega b is minus omega b cross I omega b equals 0. This cross, I've defined it here as a cross b is a half ab minus ba. In geometric algebra, it's very useful to have a half in front of the commutator. We call it the commutator product. So this thing here, which looks really simple, and is really simple, that's the whole of the Euler equations of rotational dynamics. And anyone who's done rotational dynamics will know that the Euler equation is very subtle and difficult. This is how quickly we can get to it, and you'll see how quickly we can solve it. So it's not just that you get a quick derivation, but solutions. Similar to what Hugo was saying this morning, you align the body frame with the principal axes so that your moments of inertia can just be written simply like this as numbers, ik, chi 1 to 3. And we'll call that I sub k, right? So that's the moment of inertia about the kth principal axis. And from that, you can define two constant precession rates and directions. You take the angular momentum, the space angular momentum, which of course is constant. You divide it by I1. And then you take IE3, which is, we know, rotations about the body sort of principal axis, and you get this rate, omega r, coming out. But the important bit is you've got one bivector there, one bivector there. You find the Euler equation then becomes this rotor equation. R dot is minus a half omega L, this one, times R minus a half R omega R. And the key about this, you see, one part is transforming on the left, one part is transforming on the right, and you can immediately integrate that independently each side to get what's shown here. Here's the initial attitude, and then this one here makes it rotate about the I sigma 3 axis in the body. This is an internal transformation, exactly like we were getting in quantum mechanics, and this is an external one, like that. And fully describes the motion of a symmetric top. I'm just going to risk one more video to show you this in operation. So let's find that. So this video is impressive for a particular reason. So it's not actually a video, it's a program written for Windows in 1999, which still works right now. And it was written by Christian Perwas, that some of you will know Christian quite well, who was a student of Joan Lasenby's and mine in Cambridge, and has contributed a lot to geometric algebra. I just want to show you this program still working perfectly all this time. And there's several demonstrations. This is the spinning top one. And if I move this down, this is a full slider control. I can change all the rates. There we go. You can see it a bit better there. What I wanted to demonstrate with this, I don't know how well you can see it, but there's a little picture, actually, of Christian sitting down on the top here. And there's two frequencies involved in this. You can count the rate at which this top is moving round by where the precession axis, its main axis is precessing around. Okay, count when that gets back to where it was, and then count where the picture gets back to where it was. And the two are different. And that's the two rates. One internal, there's an internal one busy rotating it about the body axis here, and then there's the external rate, the external precession, moving this whole body axis around. So there are two rates buried in that, which come out perfectly in that geometric algebra view. Okay. So let's get back to this. And the thing I just want to show you is how you can link this immediately with quantum mechanics. So, right, this next bit, this is probably one of the hardest bits of what I'm talking about. That's because I actually need to give you a bit of standard quantum mechanics, which really doesn't look very nice. What we're going to do is suppose that a particle is placed in a magnetic field. We're not worrying about the spatial dynamics. We're just looking at a particle spin in a magnetic field. Conventionally, what you do, if the magnetic field is B and the particle has magnetic moment mu, you write down Hamiltonian like that. This gamma is what's called the gyromagnetic ratio. It shows the way the particle responds to the ambient magnetic field. And you then introduce a coefficient which is complex multiplying the up state and a coefficient, which is another one complex, multiplying the down state, and that spans your state of possible quantum states. You then write down the Schrödinger equation, and you find that's the Hamiltonian is equal to IH d by dt of the state. Now, this is actually quite hard to analyze conventionally because it involves a pair of coupled differential equations for alpha and beta, which are general complex quantities. So, of course, people have done this, but it's not very pleasant. Instead, let's see what the Schrödinger equation looks like in the GA formulation. You go through this, you do translate it as I've been saying, you get this really simple equation. Psi dot is 1/2 the Dirac magnetic ratio times pseudoscalar times the ambient field times psi. And we can just plug our psi being rho to the half times the rotor into that, and you get this, and I'll multiply on the right by psi reverse. I get psi dot psi reverse. Turns out it's 1/2 rho dot plus rho r dot r reverse, and that's equal to this bivector IB. Now, it may not be immediately obvious, but this combination r dot r reverse is always a bivector. Okay? That's because if you reverse it, you can show very quickly from the fact that r reverse is 1 that the reverse is minus itself, so it's definitely a bivector. So you have bivector equals bivector plus scalar. Oh, so that scalar must vanish, and you find immediately that the rho was irrelevant. All that matters is the rotor, because the rho is fixed. And so you end up with this really simple rotor equation, r dot is a half gamma IBR. So the quantum theory of a spin-half particle in a magnetic field reduces to a simple rotor equation, and recovering this explains the difficulty of the traditional analysis based on a pair of coupled equations, because it doesn't know anything about the underlying rotor nature of what's going on. And so a solution is just immediate in a constant field. You just have the single-sided thing here that psi as a function of t is e to the, effectively, the I times the magnetic field times t over 2. So that's really quite simple. So basically, the spin vector just precesses in the IB plane at a constant rate. Now, I want to make the transition to relativistic theory now. I'm not going to go into this in as much detail. I'm just going to tell you that in the relativistic theory of spin-half particles, things are very similar. In a bit, when we get to the Electroweak theory and the strong force, I'll show you a bit more about the specific nature of the Dirac wave function. You can just assume it consists of all elements of the even subalgebra of the space-time algebra. So we can do the same decomposition. What you find is that, so it's the even subalgebra that's got 8 elements. 6 of those go in this Lorentz rotor R, which is exactly the same that we talked about before. That's the 4 meter the bivector. There's 6 bivectors, so that's got 6 degrees of freedom. Here's the rotor the half we had in the Pauli case. Here's the new bit. It turns out that when you go to relativistic theory, there's an extra duality parameter, e to the I beta over 2. And in simple cases like plane waves, you find that this tells you whether you've got particles or antiparticles. That's what it controls. But it is more mysterious. For example, in a hydrogen atom, you can work out this decomposition of the Dirac wave function, and you find that parts of the wave function are particle-like, but in other parts it's got a little element of antiparticle. So I have to say, no one really understands what the beta term in here means. And if anyone is interested in trying to take this particular thing further, there's definitely work to do to figure out what beta means in general. So I'm not saying everything's solved here, right? There's no explanation conventionally because they don't even know it exists. But we know it exists, and we don't know exactly what it does. Now you get exactly the same picture of a rigid body rotation. So now you've got the 4 vectors, the gammas that we talked about, and the Dirac wave function transforms it through to a new set, and We still have the spin vector, we have these two connected to the phase, but now because we've got a time axis, we get a new thing. And it's this. J is psi gamma naught psi reverse. That should say reverse in it. Sorry, that's a mistake. Equals rho. It turns out that's the same as rho r gamma naught r reverse. And so you just rotate the gamma naught thing, and what you get is called the Dirac current. We'll talk about its properties in a moment. Spin vector is the same as before. Rho r gamma 3, in this case, r reverse. So that's what the wave function does and what it looks like. What's the equation that it obeys? And so this is the Dirac equation, and here it is in the form first proposed by David Hestenes. It's really incredibly simple. Grad psi I sigma 3, here's this multiplication by I, the equivalent of multiplication by I, minus the charge times the electromagnetic potential times psi equals m psi gamma naught. And that's the full Dirac equation coupled to electromagnetism, all in a very simple form. And only using elements of the space-time algebra. We don't need to step out of that at all to do that. You can show quickly that that equation implies the current is conserved. And so that tells you you can't create or destroy fermions at the level of a single particle Dirac equation. That would need a high energy multi-particle process, not covered by this single particle equation. Now, the time-like component of J is positive definite, and conventionally it's interpreted as probability density, which is fine. And a normalized wave function has this, because you're interpreting it as a probability density, you want that to happen. And conservation of J implies that the probability density flows along non-intersecting streamlines, which is very useful for visualization. And I don't think I've got time to go into this in detail, but I just want to give you a little flavor of the very different view of what happens in quantum mechanics that this approach leads to. You've probably heard of the Stern-Gerlach apparatus and people measuring spin. The idea is that you take a beam of particles and you prepared them in some state that isn't specifically spin up or spin down. It's got a general mixture of spins. And they go into the Stern-Gerlach apparatus, which creates an inhomogeneous magnetic field. And you find that everything that comes out is either spin up or spin down. And the general idea in quantum mechanics is that what's happening is that before you did your measurement, this is regarded as a measurement machine, before you did your measurement, you've got the particle exists in a superposition of two states. You do your measurements, its wave function collapses to one of the eigenfunctions corresponding to the measurement process. So there's this whole idea of collapse of the wave function and measurement as being a process which is forcing something to be either one or the other, even though it was neither to start with. So what actually happens here is something that you just couldn't do normally. It turns out that if you put a wave packet in, so this is something that is representing a distribution of particles, here it is at the bottom, as time goes on, it is split up spatially into two parts, each traveling in a different direction. Here's the streamlines of the particles as they exit the Stern-Gerlach apparatus. And here's a picture of the spins of these particles. And you can see, so this is at one side, naturally, of the apparatus. This is the other side. And what you find is that the spin directions are aligned by the instrument gradually to be either up or down. And this gives you a totally different view of what's happening in a measurement process. You're not measuring at all. This Stern-Gerlach device is a polarizer, which is taking a continuously distributed initial quantity and gradually transforming it as it propagates through the instrument into either spin up or spin down. So it looks entirely classical, is what I'm trying to say. There's no collapse of the wave function. There's an entirely classical evolution of this with a perfectly good spin available at each stage. And this is not liked, this view is not liked by many people working in quantum physics. But the thing is, if you work out at any stage what would be the predictions for the number of particles that are spin up versus spin down, you get exactly the same results as standard quantum mechanics. So this is something that can sit underneath standard quantum mechanics and actually replace it with some entirely causal deterministic picture as shown just here. Anyway, now let's see how we're doing. Okay, are we brave enough to try some gravity? Yes? Okay, so gravity is one of the four forces, and normally it's considered very different from the other forces that we've been talking about, electromagnetism, electroweak, strong force. And we, in fact, in this approach, we want to make it as much like those forces as possible. So these other forces, not gravity, they're normally described in terms of a Yang-Mills type gauge theory. These are unified in quantum chromodynamics. This thing here is what the strong forces to do with. Right? The forces which bind the nucleus are called, are worked out in something called quantum chromodynamics. The chromo means that color is involved, and that's because they're meant to exchange different particles which are assigned this label, an arbitrary color, exchange particles to change their color. I'm just explaining why it says chromo. So these gauge theories sit in a flat space-time background, and they're of this particular type. It's called Yang-Mills type. Now, ordinary gravity knows nothing of that. It doesn't have any Yang-Mills structure. I'm talking about conventional gravity, and it certainly doesn't sit in a flat space-time background. It sits in, as you know, a curved space-time background. So the aim here is to have a gauge theory of gravity which is as much like Yang-Mills type gauge theory as possible and expressed in a flat space-time. So this is pretty radical, okay? We are stepping away conceptually a great deal from general relativity. Well, if it's a gauge theory, well, what is a gauge theory? It's where you have a symmetry, which is global symmetry of the problem. It could be something like global rotational symmetry, something like that. And you choose to make it local. And you say, right, in our case, we're going to choose the fact that you can carry out Lorentz rotations at a point in any way you wish. And the theory should survive that happening. So it sort of relativizes everything. And the theory should still be okay. And the answer is, the only way you can do that is by introducing extra forces, and the forces corresponding to localizing these global symmetries. So why should we want to do this? And you find that the Dirac equation, Dirac spinors, is probably the easiest place to start. So if I take spinors, psi1 of x and psi2 of x, right, these are two spinor fields, a sample physical statement would be that psi1 of x is the same as psi2 of x at all space-time positions x. That would be a nice physical statement, which makes sense. And of course, it's independent of where we place the fields in the space-time algebra. I could equally well introduce two new fields, psi1 dashed of x equals psi1, the old one, at some new position, x dashed, and same for psi2, and then these new fields, where I've done this arbitrary remapping of the space, it should have precisely the same physical content as the original. So an arbitrary remapping of space shouldn't make a difference. Same is true of fact on fields with a space-time rotor. My statement that psi1 is equal to psi2 should be the same if I stick an r in front of each, because I haven't changed anything by doing it if I do it to both, because the psi1 dashed equals psi2 dashed should have the same physical content as the original equation. And that's all fine. I can do all that. Where it doesn't work is for derivatives. I'm not going to go through this in detail. Let's just look at this one thing here, which is about what happens to rotations if I've got a derivative. So I've got r operating on psi. I wish to differentiate it. That's the same as grad r times psi, plus, I have to differentiate through this r for this grad to hit this psi. And what that certainly isn't equal to is a rotated grad of psi. So this is the key requirement in a gauge theory for local covariance, as it's called. I've got to be able to, in this case, move the rotor through the grad and come out the other, through the grad here, come out the other side, so that the derivative of the rotated object should be the rotated derivative. And that clearly doesn't work. Well, what you find is that you get round that sort of problem, and there's an equivalent one for the derivative under this position remapping by introducing two gauge fields. They're called H over bar of A, which is a vector field, and omega of A, which is a bivector field, and these are functions of a vector argument A. And you define these to have the properties so that these bad bits we didn't like in terms of the derivatives not working anymore are undone, and you get something that transforms properly. And for example, for the omega field, the bivector field, that will work provided the new bivector field rotates. You'd certainly expect that, but also has this inhomogeneous bit here. It's given my minus 2 a dot grad of r reverse. I said this structure will always give you a bivector, so it grows a new bit of bivector just here, and that takes off the bad bits in this equation here. So that's what we're doing. And it turns out then that you can wrap that up with the directional derivative in a particular direction, this direction A, which we're using as the argument, in this thing here. This is the fundamental derivative in this version of gravity. You just have, we call it a covariant derivative of A dot grad plus omega A cross. This omega A cross is this commutator product. And so this looks odd. Well, maybe not odd anymore. You're used to this by now. This is a scalar. This is a bivector operator. But it turns out that the properties of the cross operator mean that the omega cross just returns the same grade as it operates on. That means that dA, this thing we just defined here, is always a scalar operator. And in fact, it satisfies the Leibniz rule for derivatives. So that's the main part of what we need. We've actually already reached the essence of gravity in this approach, just in that really simple expression. Actually, there's one more thing that we need, because I just want to convince you very briefly that you could do some of this quite easily yourself. But if you're looking at this, you'll say, oh, what's this thing? I've defined something here, the multivector derivative with respect to A. D by dA comes into this theory. I haven't got time for the details, but the multivector derivative by vector A is just this. It's just like the gradient one we had before. You have an E upstairs mu. You now differentiate by the components of A in the downstairs frame. And this is a really nice quantity. I think Leo talked about it yesterday, and he showed you these two rules. If you're taking the dot of A with some grade R object, then the dA returns R, the grade times the object. You dualize that to this outer product, you get n minus r, n is the dimension of space. But the thing I want to show you here is this rule, which is quite a surprising one. If you differentiate through a grade R object, you get minus 1 to the r, dimension of space minus 2 times the grade times AR. And so that means that if you're in 4D space-time, and you differentiate a vector when there's a bivector in between, so if r is 2, you get 4 minus 2 times 2, which is 0. And so you're going to get 0 if you differentiate through a bivector. And it turns out this to be key to why electromagnetism is actually a massless theory, i.e. why the photon has no mass, is because of that relation. And it's key to being able to demonstrate how the Riemann tensor for a black hole works. The Riemann tensor is got by taking these derivatives I've defined and taking their commutator on any object. You get this beautiful result that the commutator dA dB on any multivector is equal to the Riemann tensor, which is a function of A and B, times M. In fact, the Riemann tensor, quite generally, it's very interesting. It maps bivectors to bivectors. It's just like the inertia tensor in doing that. So I'm not going to go through further details of this because I just want to show you what the equations of motion of the theory are. Here we are. So sorry to jump to this, but these are the full equations of the theory. Right? This is gravity. dA of this Riemann tensor evaluated on A wedge B should be 0, and this covariant derivative of the H function field, the wedge part of that, i.e. its curl, should be 0. And that's it. And this does a huge amount of the work of ordinary tensor calculus in an incredibly small space. So, for example, all the symmetries of Riemann that one encounters conventionally are encoded in the grade 3 part of this, the dA wedge, R of A wedge B. And if you want to relate this to what people have said about gravity in the past, this equation here means that in this particular approach, you've got zero torsion. That would relate it for you. So, what do black holes look like in this approach? It's always exciting to think, right, I've got something that looks really simple here. What does it do for black holes? And you can treat it exactly like electromagnetism. So in electromagnetism, if you were dealing with point charges for the first time, you'd need to choose a gauge for this A field, and you'd work from there. You want here a choice of gauge for, we start with the H function. It covers all the space, except possibly for a singularity at the origin. And just like in electromagnetism, you'd expect the field strength tensor to be the same and not depend on the choice of gauge. So I'm going to show you two of these choices of H, which are really good. They both have advantages. Neither correspond to what people ordinarily do at all, if you try to translate it through to metrics. The first one, I just have to define two things. So ER is the unit radial vector. We've got spherical symmetry, so we work with a radial vector. ET is the gamma naught as usual, but I define this new vector for one of these. It's called ET minus ER, and written E minus. And the point about this is null, all right? If you multiply that up, because that squares to +1, the squares to -1, E is null. And anyway, here's two really good choices of H, which we eventually found. H of A is A minus the square root of 2m over R, m is the mass of the black hole, A dot ER times ET. And the other one is A plus m over R, A dot this E minus times E minus. These look quite different, but both very simple. We call the first one the Newtonian gauge. A lot of the physics looks very Newtonian-like in the gauge. And the second one, because of this null vector, it turns out it's really good for treating the motion of photons, if you want to do that. Now, these would be like the A fields in electromagnetism, so we would want that the field strength tensor you derive from them, which should know nothing about gauge, should be the same. And that's exactly what you get. You find that the Riemann tensor is this mapping of bivectors. R of B is minus m over 2r cubed, r is the distance you are from the origin, B plus this rather neat double-sided sigma r, 3 sigma r b sigma r. And what's sigma r? That's the radial equivalent of a space, space-time sigma. It's E radius times E time. So here's the Riemann, which is incredibly compact, and it's so nice because you could immediately check that the field equation dA of R A wedge B, which we talked about, is satisfied. We're actually just going to do it. So we want dA of R A wedge B, so the B in here is replaced by A wedge B. So I've written it out. We want dA of A wedge B plus 3 sigma R A wedge B sigma R. We want that to be 0. Using that rule for the derivative when you're wedging with something, that first one gives 3b. All right, that was this rule back here. Right, so we've got 4 minus 1, which is 3. Just here, we expand out the A wedge B is AB minus A dot B. And then here's what I was talking about, this crucial thing. I'm differentiating the A through this bivector sigma r. So that vanishes. So I just get left with dA of A dot B. Again, you apply the rule, you just get B. But now you've got 3 of those. Work it out. Sigma r squared is 1. You get 0. So that's the complete derivation of and showing that the Einstein field equations, our equivalent of them, is satisfied in this step. So it's really impressive as regards compactness and ease of working. Now, even more impressive is doing the same for a rotating black hole. So this is the Riemann tensor for a rotating black hole called a Kerr black hole. And of course, we believe most, if not all, the black holes in the universe will have some angular momentum. And so this is probably applicable to all the black holes out there. And what you can see is I've had to make one change here. This R goes to R plus IL cos theta. L is the angular momentum of the black hole. Theta is the ordinary spherical polar theta. And this I is our space-time pseudoscalar. And so this is all still fitting nicely in the bivector algebra, because you remember when I take this upstairs and expand it in some way, the I will hit these B's, and that'll still be bivector. So I am still returning a bivector from this. If you want to check that this satisfies the equations I said, you don't need to do any extra work, because the dA thing anti-commutes with I, and so the bits that involve I, when you expand out this cube, the dA just passes through, you get a flipper sign, but since it's 0, that's fine. So actually, we've already done the work to show that this satisfies the equations. So it turns out this is quite certainly the most compact form of the Riemann for the Kerr that I think anyone's ever seen. If you look, very few authors will ever try to write down the Riemann components in the Kerr case, and they take pages if they try and do it. I mean, Chandrasekhar, for example, in the famous book, did have a go at this. No one has any idea outside geometric algebra that it's actually really simple of this form. Okay. There's a tiny bit more on gravity, which I just wanted to get in, which is to convince you gravitational waves are really simple as well. So there's a very abbreviated version of gravitational waves, but hopefully it's useful. And we just need to write down an H function, which we're going to try out, and see if it works. And it turns out to be the analog for this planar case that you want for a plane gravitational wave, the one we wrote down and said was good for photons above. Here it is. E minus is now ET minus, yes, sorry, that's the one, sorry. That's the one that we had before, where E minus was the ET minus ER. What we do here is we have a new vector. Turns out to be more convenient to work with this plus version, which is ET plus EZ. EZ is the direction of propagation, right? So I think you can see a pretty good analogy between these two. H of A is A minus a half H, A dot E plus E plus. That's all you need. You plug this in, and you find that the Riemann is, jumping forward a tiny bit, this. The G of eta is just some scalar pulse function that you put in that describes the amplitude of the wave as a function of time. That's just a scalar. And you find that the Riemann sort of machine has a bivector sat in the middle of another bivector sandwich. So it's just like the sigma r, b, sigma r we had before, but the bivector is E plus E perpendicular, where, well, what are these? E plus we defined here, that's the direction of propagation, and what's this E perpendicular? That's perpendicular to the direction of the wave, and is actually the polarization direction of the wave. So this is really neat. You take the wave direction, you take a perpendicular to it, which is the polarization direction, you form the bivector between them, and that's what sandwiches this B. And it gives you a really good idea about why it is that gravitational waves have the polarization that they do, and they react very strangely, according to how people ordinarily think about this, of rotating frames, because the gravitational wave polarization responds at 2 times the rate you'd expect. But we can see that straight away from, here's our input B coming in that bivector sandwich, here's the output B, and it turns out the output angle is the input angle plus twice this polarization direction. And that actually corresponds to the unusual nature of the polarization of gravitational waves. And we can see that coming out directly in this picture. There's a little derivation here of how it is that this Riemann tensor satisfies the equation it had to. Again, the key bit is you differentiate through a bivector just here. Can you see there's a bivector in the way? That being 0 means you only get a contribution from this bit, and when you work out what that bit gives, because E plus is null, it vanishes. So that's really nice. And something I can point out is that doing it this way, which by the way is completely exact, normally gravitational waves are done in a linear approximation. Everything I've shown you here is completely exact. And it turns out that because people had only been working with a linear approximation, they'd missed off something rather important. I call this velocity memory. And so conventionally, after a wave passes through, for example, a ring of particles, so you have a ring of particles here, this shows how they respond when the wave goes through. And when the wave's passed, conventionally, they're meant to just be sitting there and nothing's happening to them because the wave's gone. But what I found is that actually the wave imparts a net velocity to a test particle that persists after the wave has passed. And you get these rather beautiful things if you start with a ring of particles just here and let the wave act upon it. Afterwards, the particles can move off on these trajectories shown here. They're very tiny velocities, but the question is whether they will be observable in future experiments, particularly experiments done with spaceborne instruments. And so that's actually an active question. I know other people have now picked this up, that this has been pointed out, and are investigating whether there could be effects seen in future experiments. And I should say that there's another group that I should have put a reference to here, that working on this independently and conventionally, and their first publication on this coincided with when I first talked about the effect, which was about 3 years ago. And I'd only been working on this area, this particular area, for a few years, but it's interesting that it took basically about 70 years in the conventional picture to be able to see that this effect existed. So this is an interesting one, and a great deal of research is likely to concentrate on this in the near future. Now, probably, I'll try and speak no more than another 10 minutes, okay? Because I do want to get to Electroweak and strong. I just want to give you the flavor of this because it's really interesting. So, the starting point in this approach is the Dirac spinor. One finds that's always really the best place to start. And we saw gravitational forces arising by gauging the rotor transformations of the psi at the left, right? This was our starting point, and we did gauging on that R, where R is a Lorentz rotor. Where do electroweak forces come from? It appears they arise from gauging the rotor transformations at the right. And also, it's not just the rotors, there's one extra bit, which is duality transformations, e to the alpha I. So, how does this work? we need to introduce something that's already sitting there in our algebra, but I haven't mentioned yet, which are idempotents, or projectors. These things are made from the sigmas, and you have a projector, P+, which is 1/2, 1 plus sigma 3. Why do I call it a projector or idempotent? Well, multiply it out, and it comes back to itself, because sigma 3 squared is 1. You can define another one, 1/2, 1 minus sigma 3, and again that squares to itself. And these enable you to create what are called left and right-handed Weyl spinners, and you can promote a Pauli spinner phi, the type we've been talking about, to a Weyl one by multiplying by one of these. So phi, which is Pauli, goes to phi into 1/2 plus 1 plus sigma 3. This is very useful because it means you can now apply a full Lorentz rotor at the left, a full thing involving boosts and so on. Without that, it would take you outside the set of Pauli spinners, which only respond properly to spatial rotations. So putting these on the right means you can do full Lorentz rotations. And now here is a full Dirac spinner of the type we were talking about before, okay, written in terms of two Pauli spinners, and you make it up with one of these P minus things and one of these P plus things, and the phi and the omega here are Pauli spinners. And we interpolate an I sigma 2 term just here because it turns out to be useful in a moment. So there's 4 degrees of freedom, real degrees of freedom there, 4 there, so there's 8 overall, which is right. So how does electroweak theory work? It's got 2 sectors, these left and right sectors that we just talked about, which are these Weyl spinners, 1/2, 1 minus sigma 3, 1/2, 1 plus sigma 3. And it seems neutrinos, which you'll have heard about, only appear in the left sector. And so here's a neutrino wave function. The superscript P means that's a Pauli spinner, okay? So here's the full neutrino spinner, which is one of these times 1 minus sigma 3. Electrons have both a left and a right sector, and so here's the electron left sector, here's the electron right sector, and they again have at their root Pauli spinners like that. Now, this is really surprising how this works. This is, it's odd that nature does it this way, but this is how it goes. You combine the 2 left-handed components into a single Dirac wave function like this. You add the left-handed component of the electron with the left-handed component of the neutrino, and you get this thing here. And this I sigma 2 is the thing that converts the left-handed neutrino wave function into something you can use as the right-hand part of a full Dirac spinner. What is the gauging? The gauging is such that you try to leave the Dirac current, the left-hand Dirac current, psi L, gamma naught, psi L reverse, you try to leave that invariant. And that picks out the set of bivectors which compute with gamma naught. Well, we know that's I sigma 1, I sigma 2, and I sigma 3, and of course the scalar I, which reverses to itself. So actually, we're there, because the I sigma 1, 2, and 3 parts is then just a spatial rotor R, and that defines what's called the SU2 part of electron transformations, and the action of the pseudoscalar is like a phase rotation, so is U1. Okay, so that means that we've got mapping for what these transformations are, just in these very simple space-time algebra terms. And an odd thing is that nature seems only to take advantage of this SU2 part, the spatial transformations, for the left-handed wave functions. The right-handed wave functions only see the duality transformations by the pseudoscalar. So what you need then as a final object is a way of coupling the left and right sectors of the theory together. And this is the role of the Higgs field. And you might be quite surprised to realize you can understand the Higgs field, which I'm sure you've heard about, really quickly. It just pops out straight away here. So since the spinners are transforming on the right, okay, that was what Electroweak did, you can form invariant inner products between them like this. You can take the scalar part of some theta times psi reverse, because if they transform on the right, we have theta r, then r reverse psi, which just goes back to what it was. And so the Higgs field is then a Pauli spinner, H, which is a scale spatial rotor, which you use in the middle of such a product to provide a term which dynamically couples the left and the right sectors. So psi left is coupled with psi right via the Higgs field, like that. And because I said this right sector doesn't transform under SU2, it's clear that this Higgs field must provide a missing R, and so it transforms as H goes to HR. Now, I want that to be if I wanted that to be a full Lorentz boost, I'd be in trouble because H is a Pauli spinner, and that's a problem. But luckily it's not, because of course the only transformations I need are these spatial ones. So I've got a spatial transformation R here, which means that this just stays a Pauli spinner. And that's finally, well, when I first saw this, this finally explained to me what a Higgs particle was. It's a Pauli spinner, but doesn't respond to any space-time transformations, and that means that it's treated as though it's a Lorentz scalar, but it is actually a Pauli spinner. So that is what the Higgs field is. And then, finally, I'm not going to go through this, but strong forces, we can start fitting into the same idea. We just need one more thing to bring in the strong forces, which is this, that we have a Dirac spinner psi, which, as well as being a function of position x, is also a function of a linear function of a bivector. And this sounds odd to start with, but of course it's very much like a spinor version of the Riemann tensor. The Riemann tensor was a function of position, but you shoved in a bivector in a linear fashion, you got a bivector output. And it looks as though that's what's happening with the strong force, because you just need to allow your Dirac wave function to be a function of this bivector B. And then, what are the transformations of the strong force, the color force that we're talking about? It turns out that all you're trying to do is keep the inner product of the Hermitian inner product of F with itself invariant. I said the Hermitian inner product would be gamma F gamma naught, because F reverses to itself, so when you take the Hermitian thing, you just get F back. This is the thing we need to remain invariant, and it turns out that you can go through and find all the things that keep that invariant, and they correspond to generators of a group called SU3. I won't go through it now, so I've taken up too much of your time. Just want to show you one really nice thing that it ends up with, and the generators, they're called E in this approach, that you work with, three of them, boil down to being nothing more than spatial rotations of this input bivector. And this is a full finite form for a transformation within this SU3 theory. That's normally quite hard to get, but it just boils down to those spatial rotations. The other lots are not quite as pretty. This is the full form for the other sets of transformations, but it's reasonably pretty, and it's all totally expressed in spacetime algebra. So the basic thing that I want to end with is this, that we can do all of these forces, we believe, wholly with STA entities. There's only one problem with this, that it's only dealing with one generation of particles. You've probably heard there's three generations of particles. There's a pair of up-down quarks. There's then charmed and strange and top and bottom. They've formed three parallel generations. This system only seems to have room for one generation. So what are these three generations? And I'm fairly convinced that this will involve stepping outside the STA to things that are more like the conformal geometric algebra, and in particular the spaces either CL41, which I call the 1D up conformal geometric algebra, or the full conformal geometric algebra itself. So I just wanted to end with this, that these may be the space or the spaces we need for all the generation of particles, and maybe this will shed light on issues of why the left-hand and right-hand sectors are different in electroweak, because there's no explanation in what I've shown you for why that is. But I thought you'd like to know that it's good to know that an algebra that you're already using for conformal geometric algebra, 3D space, this one CL41, may actually be the key to all the forces, and everything can be done within that, which would be quite nice. Okay, thank you for listening.